Every mechanical component, from a bridge girder to a turbine blade, experiences loads during operation. But engineers don't design based on force alone. We need to know how that force is distributed inside the material and how the material responds to it. Those two quantities are stress and strain, the foundation of solid mechanics and structural design. Stress represents the intensity of internal forces acting within a material. When an external load is applied, internal resisting forces develop to maintain equilibrium. By dividing this internal force by the loaded area, we obtain stress. Stress allows engineers to compare loading conditions independent of component size and is a key parameter in failure analysis and design calculations. Strain quantifies the deformation produced by stress. It measures the relative change in dimensions of a material under loading. Unlike displacement, strain is normalized by the original length, making it independent of component size. Strain is particularly important because excessive deformation can cause functional failure even before the material reaches its strength limit. Stress and strain describe two different aspects of material behavior. Stress characterizes the internal loading state, while strain characterizes the resulting deformation. The relationship between the two depends on material properties. For elastic materials, they are linked through Hooke's law, where the ratio of stress to strain defines Young's modulus, a measure of stiffness. Consider a rubber band and a steel rod subjected to similar tensile loading. The rubber band undergoes large deformation because of its low stiffness, resulting in high strain. Steel, with a much higher Young's modulus, experiences significantly lower strain under comparable stress. This difference in stiffness is why material selection is critical in engineering design. The stress-strain curve is one of the most important characterization tools in engineering. Generated from a tensile test, it reveals elastic behavior, yielding, strain hardening, ultimate strength, and fracture. From this single curve, engineers obtain material properties required for design, simulation, finite element analysis, and failure prediction. In engineering analysis, stress tells us whether a component is strong enough, while strain tells us whether it is stiff enough. A successful design must satisfy both strength and deformation requirements. Understanding stress and strain is therefore the starting point for machine design, structural engineering, fatigue analysis, and finite element simulation.